Welcome to reinforcement learning, and we're gonna see how to deal with the very large state action spaces now. So we have taken a look at the Markov decision processes, and we used value iteration when we knew what the transition model is and also the reward model. Now in reinforcement learning, we use the temporal difference or TD target to revise our estimate of the Q function, which is a function of a state action pair. So the value function is just the maximum of those state action pair Q functions, and so this is a function of the states only. Q function is a function of states and action, and if we have many states and many actions, this becomes really a tough problem to put everything in a table. So the tabular value iteration and Q-learning is becoming really complex. And to see how quickly this becomes complex, take a look at this game of Go, where we have 361 intersections, and each of the intersections can have one of three states. It can be either empty, there could be a black stone on it, or a white stone. So you need to keep track of all of those different states. Then another example is the inverted pendulum problem, where you have a card and a pole, and the idea is, or the goal is, to balance the pole by pushing that card with some force. So the state values are then the position x of this card, the velocity of that card x prime, the angle of the pole theta, and the angular velocity theta prime. So we have a four-dimensional continuous state space, and that's really tough to put in a table. So we need different methods to deal with this. Reinforcement learning has been very successful in solving Atari games, and those have actually quite large state spaces as well. So here you see Space Invaders, I think. This game is Pong, I think. I'm not sure what this is. And here you have a breakout where you have a tray and a ball, and the ball falls on the tray and bounces back and clears some bricks here. And so for each of these pixels that you have here, those could be different states. So the whole sequence, frame by frame, produces a long vector of state values that you need to keep track on. And so in summary, we have in reinforcement learning three functions to be approximated. We want to simplify them, namely the policy function, which is a function of the states, the value function, also a function of the states, and the Q function, which is a function of a state and an actions. And so if we could simplify this, that would help the computation a lot. Now, how can we do that? Well, let's start with the states and think of the states as a vector of features x, and the x's could be the pixel value, for example. And then you might do the next natural step and use a linear regression, so a weighted function of the features to get an estimate of the Q value. Now, linear regression might be too restrictive, so we might also use something nonlinear. And here neural networks come in, because they help to approximate the Q functions, giving a real value as an output, as a function of nonlinear function of the inputs and the weights, the parameters that we're going to estimate. So let's take a look at how neural networks work. And so the idea of neural networks is to use computational neurons motivated by the human brain and write them up as mathematical functions, basically, as units. And each unit links to another unit by edges, and those edges have weights. So each unit computes actually this function z, that is an activation function h, and the activation function takes as arguments a weighted combination or linear combination of the inputs x plus a bias. And the bias shifts up and down this linear combination. And so how such a neural network can look like is shown here. So we have one input layer where we have two features, x1 and x2. Then we have a hidden layer. And what this hidden units do is they calculate the following function. They have a weighted combination of these inputs. And then we have also this bias here that feeds in here and moves it up and down. And then we apply this activation function h1 and get z, which are the hidden unit values. And so given this, we can also get to the outputs now. So we again take a linear combination, this time of the hidden unit values with some new weights, and again we have a bias that moves up and down, and then we get the output units here. So overall we get outputs from applying subfunctions of linear combinations of essentially the inputs in the end. And so what are these activation functions? Let's take a look at some common ones. So here is a threshold function that just when whatever you put in crosses the 0, so it's greater or equal to 0, is giving a 1 or a -1 otherwise. Then there's the sigmoid function, which has this exponential function here, and then whatever is in the exponential function is minus of what you put in this h function, and this squeezes actually your value that you get out of this between 0 and 1, and this crosses the vertical line at 0.5. Then there is a Gaussian activation function where you have mu and sigma that are the parameters where you can control this function. So if you increase the sigma, then you have a more widely dispersed function here. And then there's the hyperbolical tangents function, which basically also squeezes your inputs into the space between -1 and +1. And this crosses the vertical line at 0. Now, if we do nothing, just take a linear approximation, we can write that as the identity function. So the really useful feature of the neural networks is that they are a universal function approximation. There's a theorem saying that neural networks with at least one hidden layer of sufficiently many sigmoid, hyperbolical tangential or Gaussian units can approximate any function arbitrarily close, and this is great. So here's an example for using this step function here, and here you can imagine that you have a mixture of many different Gaussian kernels that produce here these approximation to this blue continuous function. And in practice, however, of course, neural networks are not as perfect as they sound, but it's still a very powerful tool. So the question is, how can we get to this weights W? So the idea is basically very similar to linear regression. So think about having a data point. For each data point n, you have a y, and then you get an output of your neural net that is denoted by f here, which is a function of the inputs and the weights. And then you minimize the distance between the two, the Euclidean distance in this case, and you can do that by many methods. The problem is that there's usually not a closed form solution, so it's a very difficult problem. So we need gradient descent methods to solve for a local extremum, a minimum, for example. And this works kind of in a very simple way. So we look at the derivative of this loss function j that we have here, or this error function, with respect to the weights. And then we get the direction of steepest descent and apply here the step size, the learning rate to it, and then we update our estimate. Now here's a picture how this could look like. So we have an initial weight here a learning rate that gives us the step size with which we go in the direction of the steepest descent. Then we get a new estimate, and we repeat this until we get to a local minimum here. So here are some references, and let's just summarize what the neural networks can do. They help us to deal with large state and action spaces, especially continuous state and action spaces. How do they do that? They help us to approximate policies, value functions, and Q functions by, for example, taking features of states to just find those patterns and predict the Q values for those states and action values. Now, basic neural network works with three components. It has weighted inputs, nonlinear activation functions, and outputs. And it can be a universal approximator, which helps us to actually solve for more complicated problems. Thanks for watching.